In this short video, we're going to review some of the ideas of the determinant. Remember that the determinant is just a number. It's associated with a square array of numbers. Sometimes we call that square array a matrix, but it doesn't have to be a matrix. We either use the letters D, E, T, or long straight lines, vertical lines like absolute value signs, around the array to denote the determinant. For a 2x2 determinant, or a 2x2 array, we calculate the determinant by first going down the main diagonal and taking the product, and then going down the other diagonal. So AD minus BC. But for a 3x3 array, we got to build up some more terminology before we can come up with a formula. So we're going to represent our 3x3 determinant by this array. Each one of these numbers inside the array is called an entry in the array. And we have a double subscript, and the double subscript are telling me the row and the column. So A sub 32 is the number that is in the third row and in the second column. We also have this idea of the minor of an array, the ijth minor. We write that as M sub ij. And how do we calculate that? We delete the ith row and the jth column, and then calculate the determinant of the remaining terms, of the remaining entries. So if I have this array as an example, and I want to calculate the 1, 1 minor, I will cross out the first row and the first column, and then calculate the determinant of what's remaining. So there's only a 2x2, so I would take 9 times 6, and then subtract off 8 times 7. And that gives me -2 for the value of that minor. Let's do another example. So the M sub 2, 1, 2, remember, is the second row, first column. So I've crossed out the second row, crossed out the first column. That leaves 4 entries left, which I'll put into a 2x2 determinant. And using my formula, I'll take 5 times 6 and subtract off 1 times 7. And that gives me what? 30 minus 7 equals 23. All right, let's take this one step further. A cofactor of a square array is, well, you have 3 things that you have to be careful of. This -1 raised to the power of I plus j just means that the sign is either going to be positive or negative. When I plus j is even, then the sign will be positive. If I plus j is odd, the sign will be negative. You have the entry at the ijth spot in the array, so the ith column and the ith row and the jth column, and you multiply that times the minor associated with that same row and column. So again, we're going to have a sign which will be positive or negative depending upon if I plus j is even or odd. We'll multiply that times the entry in the ith row and jth column, and then multiply that times the minor associated with that entry. Note that the signs are going to follow a checkerboard pattern for a 3x3 array. So in the 1, 1 location, 1 plus 1 is 2. it's an even number, it'll be positive. But then as you increase, add 1, you'll get an odd, so it's negative, then positive, and so on throughout the rows and columns. What is all this going to help us with? Well, the cofactors are a way that we can calculate the value of a determinant of any size, but we're only going to do 3 by 3s. And we just find the sum of the cofactors of any row or of any column that will give us the value of the determinant. So I put up here as a reminder our checkerboard pattern. And let's calculate the value of this determinant, expanding about the first row. So I'm going across the first row. So I have to find each cofactor and add them up. Well, the first cofactor is going to have a positive sign. So I have positive 2 times its minor. Then the second cofactor is going to have a minus in front of it. So I have minus 5. Here's our minus sign. And then times its cofactor. Let's make sure I got that right. Negative 3, 8, 0, and 6. And then the third entry in that row, its cofactor is going to be positive again. So positive 1 times its minor, which would be a negative 3, 0, and then a negative 3, 9, 0, 7. Good. So remembering the formula, I'd have a 9 times 6 minus an 8 times 7. Here I'd have negative 3 times 6 to give me negative 18. 8 times 0 is 0. Negative 3 times 7 is negative 22. Subtract off 0. And that works out to be 65. Let's use the same array, but in the same determinant, but let's expand about the first column. And again, we've got to think about our signs here. So the first entry will be positive, second one negative, third one positive, the sign on the cofactor. So 2 times its minor, which didn't change from the first example, negative 3, but now I have a minus sign in front of it. So that'll wind up being a positive 3 times its minor, and then plus 0 times its minor. And if we do the arithmetic, we get the same answer, 65. And finally, if we expand about the second column, now in the second column, my first term will be minus, my first cofactor will have a negative sign. The second cofactor will have positive sign, and the third cofactor will have a negative sign. So I have a negative 5 times its minor, a positive 9 times its minor, and then negative 7 times its minor. And working that out, again, I get the same 65 as an answer. Now, some properties of determinants. For a 2 by 2 determinant, the area of the parallelogram determined by the vectors of the row entries is the absolute value of the determinant. So a determinant can be positive, negative, or 0. And so the area here would be, you have to take the absolute value. And so as an example, if I look at 1, 2, negative 1, 1, so my blue vector has components 1, 2. My red vector has components negative 1, 1. The determinant here is 1 minus a negative 2, which will make 1 plus 2, which equals 3. And then if you look at this parallelogram as being two triangles. The base of each triangle is the diagonal, which has length 3. The height of each triangle has height 1. So you can verify that the area is indeed 3. If you exchange any two rows or any two columns in the array, then the determinant just changes sign. So here's the determinant we used with our examples, and we found that when we expanded about either the first row or the first column or the second column, the answer was always 65. But if I exchange the first and second rows, then the sign is going to be negative. I'll get negative 65. And the same thing is true, if I exchange the first two columns. Instead of positive 65, my answer will be negative 65. And finally, the absolute value of a 3 by 3 determinant is the volume of the parallelepiped determined by the row, the vectors consisting of the row entries. Now, what's a parallelepiped? Parallelepiped, you can think of it as like a squished box. My 3 vectors here form kind of one vertex of the box, and then I just fill out the other parallelograms in order to make, well, I'll have a bottom and a top, a front and a back, and then 2 sides. So it's the 3-dimensional equivalent of a parallelogram, and it's called a parallelepiped. So I hope this review of determinants is helpful. We're going to see this in conjunction with several things, but one of the most important things is the cross product.